All right, today we're going to be graphing logs and doing transformations of logs. In order to do that, we want to recall a couple things. We'll start with the exponential, y equals b to the x, and it looks like this. We said its key points for this exponential was 0, 1. Doesn't matter what number our base was going to be here, we're always going to have the point 0, 1, because anything to the 0 power gives us 1. Now, when we raise that to the first power, we're going to get itself. So our second key point is 1b. That gives us this point right here and this one here. Now, our horizontal asymptote, because this has a horizontal asymptote, is at y equals 0, this x-axis. Now, last class we learned that a log is the inverse of an exponential. So if we had log base b of x here, its key points would then have to be 1, 0, and base 1. Because with the inverse, we're switching that x and that y. So our new key points would be these points here. If we've got the point 1, 0, and base 1, this is going to get close to the y-axis and then move this to the right. In this case, we have a vertical asymptote at x equals 0. Horizontal lines are written as y equals, vertical lines are written as x equals. These are inverses of each other, so they're a reflection over that y equals x line. We see that here in these two pictures. This would be considered our parent function for our logs when we use transformations here. So with our logs, we're going to look at them. We're going to have our key points at 1, 0, base 1, because that's the switch of the exponential. And we're going to have vertical asymptotes, so we're going to write those as x equals 0. So we'll start working with that in order to do transformations. All right, so let's talk about this general form of the equation for our transformations. A is in front of the log. B is factored out inside of the argument. And then we have x minus c also inside the argument, our closed parentheses, so plus d is outside of the argument. A couple things we've talked about. When there's no base written here, we said that is the common log and it has a base of 10. So we want to keep that in mind right here. So we're using that one for our parent function here. The a is on the outside. It's being multiplied on the outside. So all of this is one term. That log b x minus c is all one term, and it's being multiplied times the a, so that's still part of that one term. And then we're adding that d at the end, so that's going to be separate to that one term. Just a quick review on what the effects are for a, b, c, and d, and we will focus mostly on a, c, and d. Those are the biggest ones used for exponentials and logs. We will not use that b as much. The only thing we'll use it is that negative there. So with the a, when it is negative, it is a reflection across the x-axis. So if the negative is out here where that a value is, then that is a reflection across the x-axis. If the negative is on the inside of the argument right here, then it is a reflection across the y-axis. So that's the difference between those two. If my a value is greater than 1, it is a vertical stretch. And if it is between 0 and 1, it is a vertical compression. For the c value in here, when it is written as x minus c, that is to the right c. And when it is x plus c, it goes to the left c. One of the big things, though, that we've been missing in the past is we're forgetting to factor out. So if it is just written as negative x plus 2, you want to keep in mind that you need to factor out that negative. It must be factored out like this in order for these transformations to work. Then plus d is up and minus d is down. So those are our transformations. We've been doing those all year, so you should be comfortable with moving the graphs now with these transformations. All right, so we're going to start. And we use the exponential y equals 2 to the x quite often. So we're going to start with that parent function y equals log base 2 to the x, which is the inverse. So we'll start with those points right there. We said all logs are going to have the point 1, 0, because that's the switch from 0, 1 to 1, 0. And in this case, the base would be here because that's what switched. So our base in this particular one is 2. If we talked about this one, the base is 10, so this would be 10, 1. So whatever that base is, it's going to give you that second point. So we've got a point at 1, 0 here, and then we've got a point at 2, 1. We've got a vertical asymptote on the y-axis, so this gets really close, and then it shoots out to the right there. All right, that does affect our domain. We have no values in the negative. That's because you can't have a negative argument here. That doesn't exist. So we don't have any negative values. It is only getting close to the y-axis, so we do not have a 0 for an x value. So this would be from 0 to infinity, and it would not include 0, so we would have a parentheses. Now this does keep going down forever and up forever, so this range is all real numbers, which can also be written as negative infinity to infinity. All right, I do want to show you that on the calculator. As a reminder, if you use this log button to the left of 7, so the log button to the left of 7, that's a base of 10. Anytime you push this button here, it's going to be a base of 10. If you can't remember that, there's that 10 right above it. All right, so let's look at putting this in the calculator. This particular log has a base of 2, so I would not want to use that button since that has a base of 10. I would hit alpha window and then go down to our log base there. That's going to allow you to put in any base you want. And so this particular one had a base of 2, and then we're going to put in an x there for the argument. We hit graph, and there is our graph. A couple things I want to point out. So the calculator can't graph a vertical line. Its pixels are not quite as good as your HGTV there. So it looks like it shuts off right there. I'm sorry, you guys are getting a glare. All right, so it looks like it cuts off right there. That's only because of the calculator screen. It is not cutting off there. It does continue down all the way following that y-axis. Again, your calculator just can't graph below that. So make sure you don't think that it cuts off there because it does not. All right, so let's look at our table here. So I hit second graph and I look at the table. I see that at 0 it says error, and all of our negative values say error. You cannot have a negative argument and you can't have an argument of 0. It starts after that. So we see our point at 1, 0, which we said that was one of our key points. And then you see 2, 1, and then it starts to go up from that point there in order to graph it. It will continue going forever. So that makes our graph right there look like this and then keep going forever to the right. All right, now that we've graphed this parent function and reviewed our transformations, there's a couple things we want to remember. Remember 1, 0, and base 1 are the key points that you want to use in order to graph, and that the log of 0 is an error, our first error there, and that is what creates our vertical asymptote at x equals 0. So with the log base 10, you can always remember 0, 1, 10. But the big things, 1, 0, base 1, and then your vertical asymptote. That will allow you to graph any log. All right, so let's look at graphing one of these. We'll start with this easy one over here at number 1. It says log of x minus 1 plus 2. Now I want to think about the 1, 0, the base 1, and then our vertical asymptote. And I usually start with the vertical asymptote because that's the easiest way to get our graph on the paper. So if we think about our asymptote right here at x equals 0, when I move up or down, it is not going to change my graph. When I stretch or compress or reflect, it's not going to change my graph. But if I move to the left or right, that is going to change my graph. So I want to think about this left and right movement is going to change the vertical asymptote. So you want to think about that. All right, so when I look at this, I've got two transformations. I've got one right here at the 1, and then I've got one right here with 2. This is x minus 1 inside of the argument, so that's my left to right movement. That is going to move to the right 1. And we just said that changes the VA, our vertical asymptote. So our vertical asymptote is going to be at x equals 1. It was at 0. We're going to move it to the right 1, so it's going to go to x equals 1. And then that is up 2 since it's in the place of d. So I start by graphing my vertical asymptote here at x equals 1. And then I think about my other 2 points. So the first one would be at 1, 0. That's this point right here. I'm going to move it to the right 1 and up 2. And then I'm going to move the next point over, which in this case would be 10, 1. Since our base is 10, there's no number written here, so that's going to be 10, 1. I'm going to move that to the right 1, and that's off my graph, and up 2, and there's my next point. And so there's my log. Its domain in this case would be from 1 to infinity, since it's starting at that vertical asymptote moving to the right. And then our range for all logs is all real numbers. That's the switch from exponentials. All right, for our number 2 here, we have 3 transformations in this one. The first one is that negative. That gives us a reflection across the x-axis. We've got the left one from this inside part here, and then we've got a down 3. That left one is the one that changes my vertical asymptote. It is going to be at x equals -1. So we start by graphing that. Now we run those transformations through our key points. So we've got that 1, 0. If I reflect that over the x-axis, it's not going to go anywhere since it's on my x-axis. I move it to the left 1 and down 3. And there's my first point. I do the same thing for my 10, 1 point. I reflect that over the x-axis. That one will reflect, so we go down to 10, -1. We move it to the left 1 and down 3. And now we move towards our asymptote. This point is lower than this one, so it is going to move out this way and then go towards the asymptote here. That's what that reflection across the x-axis looks like. Now for our domain, it is going from -1 to infinity, since that's where my vertical asymptote is, and it's moving to the right, and all logs have all real numbers. All right, on this next one, we're going to look at the reflection across the x-axis, because in this case, the negative is on the inside part here. Now, before I can get started, though, I have to go ahead and factor that. It must be in this transformational form in order to look at the transformations. So here we go. We have y equals log. I'm going to factor out this negative so that it looks like this. I have factored out the negative. Negative times x is -x. Negative times -2 gives me a +2. Now I can determine my transformation. So the first one is going to be that reflection across y. The second one is going to be to the right 2, since this is x -2. That's that big mistake we keep seeing on quizzes and tests. Here, people are putting left 2. This does not go to the left 2. This goes to the right 2 because it must be factored out. And then our last one, down 1. What changes our vertical asymptote is that right 2, so that is going to be at x equals 2. So here is our vertical asymptote. That's always going to be the first thing you want to graph. Then we start at that point 1, 0. I can reflect that across the y. It would go over here to -1, 0. Then I move it to the right 2. Happens to land right in the same spot, and then down 1. I do the same thing for my next point, which was 10, 1. I reflect it across the y, and that goes to -10, 1. I move it to the right 2 and down 1. This point is above this one, 1 unit, and so I'm going to move it towards the asymptote this way. That does change our domain. It is coming from negative infinity up to 2, so our domain is going to look like this instead. We always put the smallest number, which in this case is negative infinity, to the biggest one. And our range for all logs is all real numbers. All right, we're going to do one more here with a stretch now. This 2 up here gives us a vertical stretch by 2. Then we've got a left 3 and up 4. The one that changes your vertical asymptote again is that left 3. So we're going to start by graphing our vertical asymptote at -3. Now we're ready to use the other points. So the first point at 1, 0, when we vertical stretch, that means we want to take it from here and pull vertically. That's a vertical stretch right there. So we would multiply the y values times that scale factor. If I multiply 0 times 2, it is still 0. So that's not going to change our first point. I can move to the left 3 and up 4. Now my second point that was at 10, 1. When I multiply 1 times 2, I get 2. So it's going to bring it up here. Then I move it to the left 3 and up 4. What that's done is, instead of just going up 1 unit, so if we follow this one here, instead of being up 1, it's up 2. It is doubled. That's what that vertical stretch has done. And so now we're going to get close to the vertical asymptote and then move towards that point. It's a little bit steeper. That's what that's done to my graph. All right, now we're going to go backwards and we're going to write the equation from a graph. You want to use those same transformations. You're using those again in order to write the equation. So the first one you should look at is that vertical asymptote, because that's the first one we use to graph. So I see here my vertical asymptote has to be at this point right here at x equals -2. That's where it's flattening out and following it along forever. So now I've got a vertical asymptote at x equals -2. So I know it's moved to the left 2. The next thing I want to check is to see where my 1, 0 point went. So at 1, 0 right here, if I move that to the left 2, it'd be right here at -1, 0. That is not a point on my graph, so I know there's another transformation. It has gone down 2 to get to this point right here. So that is another transformation that I need. All right, the next point we're given here at 8, -1, this point right here, these are 9 units away and 1 unit up. And so we know that that's our parent function log base 10, because that's what it is on our log base 10 parent function. And so there's no stretch or compression here, so we would get log of x plus 2 minus 1. And so our domain would be from -2 to infinity, and our range would be all real numbers. Here's another one for us to try. Our vertical asymptote is at 5. So we know this has moved to the right 5. Our point right here would be the 1, 0 point. So we're going to move that one here from 1, 0. We know that it's moved to the right 6. I'm sorry, to the right 5, and then up 3. So we went from 1, 0, moved it to the right 5. We already knew that one because of the vertical asymptote. And then we moved it up 1, 2, 3 to get it on the graph. To check the next point over, it went over 9 and up 1. And so we know that that's that parent function again, has not moved. So we get log of x minus 5 plus 3. All right. We're going to do a quick review of some of the things that we've gone over in the last couple days to make sure that everybody's still on the same page on knowing. So we've talked about an exponential and a log are inverses of each other. That's important. An exponential and a log are inverses of each other. So anytime that you find the inverse of an exponential, you should end up with a log. And anytime you find the inverse of a log, you want to end up with a exponential. So we'll practice here. In order to find the inverse, we switch the x and the y. And then we're going to solve for this y. Well, the only way to get the y out of the exponent, so freeing it from there, is to use that definition to convert this to a log. So I'm going to drop the base here, and that gives me a log with a base of 2. And then they switch, so the y plus 1 is freed, and the x becomes my argument. That's how we get this out of the exponent, by using that definition. My last step is to subtract the 1. And so we get y equals log base 2 of x minus 1. This is not in the argument. The x was by itself, and this was one whole term that we're subtracting the 1 from. So this is not part of the argument. That would be on the outside. All right, we're going to quickly graph those just so that you can see that they're inverses as well. So this is an exponential that's moved to the left 1. And so here is our graph. And this is a log with a base of 2 that's gone down 1. And so there is our inverse graphs. Notice that they're a reflection across that y equals x line. And so the domain of exponentials is all real numbers. The domain of the inverse is from 0 to infinity, which was the range of this one. All right, here's another one to try. We switch our x and our y. The first thing I want to do is add that 1 so I can get that one term by itself. And so we get x plus 1 is equal to log base 2 of y plus 3. This is all one term. So the only way of freeing this out of the argument is to convert it to an exponential. And so I'm going to move that over here. So I drop the base because the base on the log is the base on the exponential. This becomes my exponent, and the y plus 3 is freed. My last step would be to subtract that 3. And so we get 2 to the x plus 1 minus 3 is equal to y. All right. We'll move over to just some basic log and exponential stuff that you need to know. Log base 10 of x is the log x. So when there's no log written there, no base written on the log, then it is a 10, and it is called the common log. The number 2.718281284 that continues to go is written as e, and it is a number, not a variable. So keep that in mind. 2.718, which I told you we can learn as 2.72, is e, and it is a number, not a variable. A log with a base of e, x, is equal to the natural log of x. That's what this is right here. This ln x stands for the natural log of x. And that is a log with a base of e. Remember, that one also has a button to the left of the 4. That's the natural log right there. And if you forget, that is a base of e right above it. So natural log is a log with a base of e. If you remember those, you can remember these identities here. A log with a base of b and then b to a power are inverses, so they cancel out, and that would give you 1. The common log has a base of 10. With a 10, again, that cancels out and gives you 1. And the natural log is a log with a base of e, and e to a power would be inverses, so that cancels out and is 1. So those are some easy identities to remember, as it helps you simplify when we start solving next.